Now that we've introduced enthalpy, let's talk about how we incorporate that into a chemical equation. So let me give you an example. Let's say you have an ice cube melting to form liquid water. So the reaction would be this. You've got water that's a solid, and it becomes water that's a liquid. Now, because this is an endothermic process, both Q and delta H will be positive values. So to incorporate the enthalpy into this reaction, there's two different ways of writing this. We could say this, that we can take the reaction that solid water becomes liquid water and say that delta H is equal to a positive 6.01 kilojoules per mole. Okay, so this is a standard chemical equation. Another way to do this is actually to take this enthalpy number and actually incorporate it into the chemical equation and say this, that the water, which is solid, now since the system is absorbing the heat, this number, the 6.01, would actually be on the left-hand side of the equation, so we would say that solid water plus 6.01 kilojoules per mole yields liquid water. Okay. Now, this equation that we just wrote, this is called a thermochemical equation. So it's just a normal chemical equation. The only difference is that there's heats or there's enthalpies involved. Okay, so let me take a look at another one. What if you had another reaction that said this, that you combusted methane? So you had the CH4 gas plus O2 gas, 2 moles, yields CO2 plus H2O, 2 moles. Okay. Now, if I wrote it the other way, delta H is equal to negative 890.4 kilojoules per mole, this is also a thermochemical equation because we've got the enthalpy value associated with the chemical reaction. So these two reactions, depending on either way you write it, doesn't matter, as long as you've got the enthalpy value somewhere in the equation, these are called thermochemical equations. And so we treat these enthalpy values as if they're part of the chemical equation. So if we're doing stoichiometry, we just treat it as if it was a reactant or a product. So the following guidelines are helpful in writing and interpreting thermochemical equations. So the first part, this is extremely important. Specify all states of matter. So this is really important because going forward, we have to know if water is a liquid, a solid, or a gas. So that's extremely important. We got to know that. The second step, if we multiply both sides of a thermochemical equation by some factor, which we'll call n, you must also multiply delta H by that factor as well. All right, so let me write that down. If we multiply both sides of a thermochemical reaction by some factor, and we call that factor n, you must also multiply delta H by that factor. Okay. Finally, if you have to flip an equation, so let's say instead of having reactants going to products, you have to write it as products going to reactants. So you have to rewrite it backwards. If you do that, you must also flip the enthalpy sign. Okay. So if you flip the equation, so meaning products become reactants, you must also flip the sign of the enthalpy value. So if it's positive, it becomes negative, or negative becomes positive, depending on how you've got it. So let me show you how this all works. So here is a problem. Calculate the heat involved when 266 grams of white phosphorus, P4, burns in air according to this equation. So we've got the thermochemical equation, P4 plus 5O2 yields P4O10, and we've got that enthalpy value. So what we're going to do is treat this enthalpy value as if it's part of the reaction. Now, because this is negative, that tells us that this is being released. So this is an exothermic reaction. So in other words, this would be almost like another product. All right, so we're told we have 266 grams of P4. What we need to do is to convert from grams of P4 to moles of P4. All right, and so we have to use that molar mass of P4. So 1 more P4 is equal to 123.89 grams of P4. So that way the grams of P4 cancel out. Now here's where it gets a little tricky. We want to go from moles of P4 to the heat. And the unit tells us kilojoules per mole. So we're going to use the stoichiometric coefficients. You've got a 1 mole of P4, you got 1 mole of the heat. So what we're going to say is that for every 1 mole of P4, and that goes in the bottom, we're going to have negative 3,013 kilojoules. So that way moles of P4 cancel out, and there's our heat. All right, so if P4 had 2 moles, instead of writing 1 mole, we would write 2 moles. All right, and this is equal to negative 6,469 kilojoules. And that's it. A thermochemical equation is just like a normal chemical equation. The only difference is you have an enthalpy value that goes along with it. But you treat it just like you would as if it was a reactant or a product.